In a damped system, the system's response is attenuated due to energy loss. As a result, the system response UU, as well as the results from the eigenfrequency analysis, take the form of complex numbers. In this context, the real part of the complex eigenvalue represents the natural frequency of the system modified by damping effects. Meanwhile, the imaginary part corresponds to the energy dissipation caused by damping. The quality factor, or Q factor, of the system can be calculated as follows. In this video, we will cover the following topics. First, we will demonstrate two methods to a damping to a cantilever beam in order to create a damped system. The first method involves defining an isotropic loss factor, which determines the amount of energy dissipation within the system. The second method uses Rayleigh damping, which allows us to define energy loss as a function of frequency. Next, we will define the material loss and perform an eigenfrequency simulation to obtain complex-valued eigenfrequencies. Using these results, we will calculate the damping ratio and the Q factor of the system. Finally, we'll show how to create animations for each of the resonant modes to visualize the dynamic behavior of the structure. For the geometry, we will use the same cantilever model that was used in the previous eigenfrequency simulation of the undamped system. In the parameters section, we've included the original values for length, width, and thickness, and added parameters for damping including the loss factor and Rayleigh damping coefficients. Next, we need to add damping to the linear elastic material. For the damping type, the simplest approach is to define an isotropic loss factor. However, if you want to account for frequency-dependent damping behavior, you can choose Rayleigh damping instead. In the case of Rayleigh damping, you normally need to input the alpha and beta coefficients, which are typically obtained through experimental measurements. However, in this example, we've used arbitrary values that result in a system Q factor of approximately 1000. The mesh and study settings are the same as those used in the previous file. Once the simulation is complete, you can extract the frequency, damping ratio, and Q factor using the expressions provided in the eigenfrequencies node. Finally, we'll show how to create animations of the resonant modes obtained from the simulation. Alright, let's get started.